All right, let's take a look at another linear transformation. Again, we're mapping from R2 into R2. So our matrix representation for this linear transformation is matrix A has column number 1, which is -1, 0. Column number 2 is 0, 1. So here we're given the matrix A. And we want to think about what effect is this transformation, which is defined by matrix A, going to have on our friend, the blue elephant down here. So let's take a look at what's going to happen to these standard column vectors. So from this matrix, we could also operate the other way, that this first column is going to tell me where this goes, where E, the first standard column vector, goes, and the second column, right, this tells us where the second standard column vector is going to get mapped to. So let's kind of illustrate those. So we have the vector E1, which is 1, 0. And so under this map, this vector is going to get flipped over here to -1, 0. Whereas standard vector 2, which is 0, 1, it is not going to get mapped anywhere. So in this case, each of these vectors, we're going to change the x-coordinate. We're going to change the sign of the x-coordinate, or the first entry of the vector, and we're not going to do anything to the y-coordinate of the point in R2. We're not going to do anything to the second entry in the vector. And the result is a flipping around of the elephant. So now this elephant has flipped around, and this is what we would call a reflection over the y-axis, or in this case, we can call that the x2 axis. And in the textbook, they have other types of reflections that I would encourage you to take a look at. So you can think about what happens when we reflect over the x1 axis. We could reflect over both of those axes. We can reflect around the origin. We can reflect around the line y = -x. So there are other types of reflections that we could similarly apply to R2 by picking the right matrix A up top. And let's take a look at another type of linear transformation, which in this case would be an expansion, but they could be a contraction. And so I want to just highlight that this is different than the dilation that we first looked at. The dilation was a diagonal entry where matrix where both of the values were the same, right? There was a 1/2 here and a 1/2 here, and that resulted in shrinking the elephant to scale. So now let's think about what happens if one of these is 1 and the other one is 2. And first we can think about what happens to the standard column vectors E1 and E2. So E1 is not going to get moved anywhere. And here we have the same blue elephant as in the previous examples. It's just been put in a bigger grid, right? So now our grid is going up to 2 and down to -2 and so on over here, because I want to take into effect that we're going to expand this elephant. So we start with an elephant over here, and E1 is not going to get moved anywhere. E2, however, is going to get shifted. So if it started over here, it now becomes twice as long. So we're going to stretch in the x2 direction. And we're not going to do anything in the x1 direction. And we're going to stretch in the x2 direction by a factor of 2. And that is going to have a slightly different result in that we're now going to ruin the scale of the elephant. So we haven't done anything in the x1 direction, but we are taking this elephant and we are stretching it in this direction, right? In the vertical direction, in the x2 direction. And so this we would call, in this case, an expansion, because we're stretching it out. If this value 2 were less than 1, then that would give us a contraction. And this is, again, different than a dilation because the factor that we're stretching in one direction is different than the factor in the other. We're only stretching in one direction, in this case, the x2 direction. And I would encourage you to take a look at the textbook. They have other contractions and expansions. For example, what happens when we contract or expand in just the x1 direction and not the x2 direction.